All right, in today's video, I'm going to be going over how to use the metric measuring system, sometimes called SI. To measure length in SI, we would typically use a ruler, just like in the English system. The ruler would be divided into centimeters, and frequently those centimeters will be graduated into 10 millimeters for each centimeter. So a millimeter is 1/10 of a centimeter. So if you look at the picture here, the scale that's at the top along that ruler is the metric scale. You can see the centimeters, and each centimeter is divided into tenths. Since it's divided into tenths, we call this a decimal scale. So anytime your unit's divided into tenths, it's a decimal scale. So when you look at this, if we were to zoom in on it, that smallest increment on a metric ruler is going to be a millimeter. Frequently, the 5 millimeter mark will be a little bit longer. And then the numbered marks are going to be your centimeter. Whenever we make a measurement, there are several parts to it. The measurement always includes a value, units, and some kind of indication of uncertainty. We can never measure anything perfectly. A measurement is just our best estimate of what the actual value is. I'll show you what I mean. Let's say I wanted to measure the length of this rectangle using this white box. There's no markings on this white box, so it's kind of hard to use. But let's say I knew that the white box was 10 centimeters long. Based on that, I could guess that this purple box is somewhere around 2 centimeters long. It's a pretty rough estimate, but still, I can kind of guess that it looks like it's about that long. But if I added some markings to it, I could see, yes, it is 2 centimeters long. It's in fact a little bit more than 2 centimeters long. So now I've added marks for every 1 centimeter, and I look at it, and again, I could kind of guess that based on where it falls now, maybe it's about 2.1 centimeters, maybe 2.2, somewhere in there. But if I added the millimeter marks, I could get even closer. And I could see, it's a little bit more than 2.1. And I could again estimate, it must be around 2.1. That looks like about halfway, so maybe 2.14, 2.15, something like that. But is this even the true value of that rectangle? If I could get even a better measuring device, I might be able to get even more digits in my measurement. I could get even smaller decimal points, and I would be closer to the true value. So none of these were necessarily a wrong measurement. It's just some of them are a better estimate of how long that rectangle actually is. And with a better device, I could get even better. So that's what I mean when I say all measurements have some uncertainty. Even though we know this rectangle is 2.13 or so, or 2.14, we don't know that it's exactly 2.14. In fact, we know it's probably not. So, taking that in mind, how long is this rectangle? Well, let's take a closer look, zoom in, and we'll see that this rectangle, it comes to about, goes a little bit past 3.8. So we know it's going to be 3.8, that's certain, but it's between 3.8 and 3.9. So how far past 3.8 is it? In this case, we might estimate, again, it looks about halfway like the last one. So maybe 3.84, 3.85. Those would probably be acceptable answers for this one. So our best estimate on this is 3.84 centimeters. The 3 and the 8 are certain. We know for sure it's 3 centimeters, and we know for sure that it's 0.8. The 4 is uncertain. I kind of guessed at that. And so this number indicates how certain we are. We know that the 3 is certain. We know the 10th place is certain. The 4th place, or the 100th place, is uncertain. So we use what is called significant digits to indicate the uncertainty of a measurement. Significant digits are digits in a decimal number that carry meaning and indicate the certainty of the value. So whenever we record, whatever we record, everything that's recorded is considered significant. And we always want to make sure that we include all the certain digits from our measurement and one uncertain or estimated digit. And that tells us how good that measurement is, just by how many decimals that we write. So I'm going to give you one last example to kind of show how this works. But first, I'm going to explain how measurement, our rules for different measuring devices. So if you have a digital instrument, this would be an instrument with a screen that displays a number. You just write down that number. Whatever that screen says, we record all digits, including zeros, after the decimal point, exactly as displayed. And we know that all those are significant. The last digit on that screen is assumed to be uncertain. Now, on decimal scaled instruments, like the meter stick that has units divided into tenths, we record all the digits that you can certainly determine from the scale markings and estimate one more digit. Okay, and so we're going to look at one more example of that. And here we go. So from here, we can see with this, I have markings for centimeters and millimeters. So centimeters plus tenths of a centimeter. And I look at this box and it looks like it's pretty much exactly on the 1 centimeter mark. So how would I record that? Would I record it as 1 centimeter? Well, actually I wouldn't, because this would imply that the 1 is uncertain. And I am certain about the 1 because this device has a marking for whole centimeters. So I would not write it like that. Would I write it perhaps as 1.0 centimeters? Well, no, this would also not be correct because this would imply that the 0 is uncertain. And in this case, I know for sure, because I have markings for a tenth of a centimeter, I know for sure that it's less than 1.1 centimeters. I know for sure that the tenths place is a 0 centimeter. So I would actually write it as 1.00 centimeters. I accidentally left the units off there. I'd write it as 1. So that last one's wrong too. It should be 1.00 centimeters. This would say that we know for sure that the 1 is certain, that there was a marking for that the 0, the 0.0 is certain because there's a marking for that, but the hundredths place 0 is uncertain. Maybe that's really 0.001, maybe it's really 0.002, but there is our uncertain digit.